In this video, we're going to talk about how to calculate probabilities using counting. So many experiments, especially the ones we were working with in the last video, have a common property that their sample space is what we call uniform. So what we mean by uniform sample space is where each of the outcomes, so every outcome in the sample space has an equal chance of occurring. So they're equally likely. So these are the ones that we made use of in the last video where I was relying on your intuition. So for example, the obvious ones, okay, so flip a coin. Now, as long as it's a fair coin, okay, the sample space has heads or tails, and they're equally likely to occur. If you roll a fair die, the sample space is 1 to 6, okay, and they're all equally likely to occur. So those are examples of uniform sample spaces. Now, the benefit of having a uniform sample space is if you have, say, capital N outcomes in your sample space, so N of S is capital N, and your sample space is uniform, they're all equally likely. So that means that each probability, so SI is just some random outcome in your sample space, each one is going to have probability 1 over N. Okay, now if you're not sure why, so we should have each of these probabilities, so P1, remember, is the probability of S1, P2 is the probability of S2, so if we add up all of these probabilities, we should get 1. But all of these probabilities are actually equal, so we're adding up the same number N times. Okay, and that should equal 1. So that means that we actually have N P's, and then if we solve for P, it has to be 1 over N. Okay, so each outcome in the sample space should be 1 over the number in the sample space. So remember, we did the example, we made a probability distribution table for the fair die, and each of these outcomes had probability 1 over 6, which I was hoping that you believed me at the time, but this is why. It's because we were in a uniform sample space. Now, if we're in a uniform sample space and we have event E, where E has K outcomes in it, okay, it doesn't matter if they're the first K, just any K outcomes, then if I want to compute the probability of E, it's going to be these probabilities added up, so P1 plus P2 up until Pk, so the probabilities of each outcomes. But each of these are 1 over capital N. Okay, so that means that I'm adding up 1 over capital N K times. Now, when we're adding fractions, we have a common denominator, so we can just add the tops. So 1 plus 1 plus 1, K times, is just K. So we're going to have the probability of E is the number of elements in E divided by the number in the sample space. So here you can see where the counting is likely to come in. So just to rewrite that again, so if we have a uniform sample space S that has capital N outcomes and E is any event, then the probability of E is going to be the number of things in E divided by the number of things in S, or capital N. Okay, now it's important that we're in a uniform sample space. Okay, so if the sample space is not uniform, then this doesn't work. So we want to be careful about that. So let's try an example that's a bit more complicated than just rolling a die. So a box contains 3 yellow, 3 blue, and 2 green marbles. Okay, so that gives us 8 marbles in total. Now, it doesn't say the marbles are different, so I'm assuming that the 3 yellow marbles all look the same. Okay, and we want to draw 2 marbles. Okay, so not just 1, but 2 of them at random. Here they're asking us, what's the probability that both the marbles are yellow? So before we can even try to compute the probability, we need to think, what's the sample space here? And is it uniform? So I'm going to call this S1. Maybe let's do it in blue. So the proposed sample space, I'm going to try and propose something, and then we'll talk about whether it's going to work or not. So because we're grabbing two marbles at random and we're just going to have a selection, the order I select them doesn't matter. And because each colored marble probably looks the same, okay, unless they're numbered or something, it's going to be hard to tell the difference between the three yellow marbles. We might think that the sample space is going to look like something like this. So we could get two yellows. We could get a yellow and a blue, a yellow and a green, a blue and a blue, a blue and a green, or two greens. Okay, that's every possible combination of two colored marbles. Okay, yellow, blue, and green. So that is a valid sample space for this experiment. But is it uniform? So I'm going to try and illustrate this because we can't compute the probabilities, but intuitively, do you think the probability of, say, getting yellow, yellow, how does that compare to the probability of getting green, green? Okay, so now we have 8 marbles total. 3 of them are yellow, 2 of them are green. So in order for green, green to happen, I need to grab 2 specific marbles. But in order for yellow, yellow to happen, I need to grab 2 of 3 of the marbles. So there's options. I can get 3 yellow marbles in sort of multiple ways because there's 3 to pick from and I only need 2. So with that argument, we probably are comfortable saying that the probability of yellow, yellow should be bigger than the probability of green, green. Okay, but these are 2 different outcomes in our sample space. So because they have different probabilities, this is enough to say S1 is not uniform. Okay, now this is unfortunate, but we can still compute these probabilities. All we need to do is rethink our sample space. Oops, I don't want to call it S1, let's just call it S. Okay, so let's just rethink our sample space. So instead of using S1 that I wrote in blue here, what I'm going to do is imagine that all the marbles are distinct. Okay, so then my sample space is going to have yellow 1, yellow 2, yellow 1, yellow 3, yellow 2, yellow 3. Okay, so there's 3 different ways to get yellow, yellow. Or I could have yellow 1, blue 1, or yellow 1, blue 2, or yellow 1, blue 3. Okay, and then all with yellow 2, okay, etc. Okay, so what we're going to do, okay, so instead, imagine we can tell the difference between the marbles. Okay, so that yellow 1, yellow 2 is a different outcome from yellow 2, yellow 3. Okay, now the order I picked them still doesn't matter, so notice that I didn't do yellow 2, yellow 1 because it's already there with yellow 1, yellow 2. Okay, so it's still, we're just getting a selection of marbles, so the order doesn't matter. All I'm doing is supposing that the colored marbles, you can tell the difference. So imagine that they're sort of numbered or something. This S is uniform because now if you take 2 random outcomes in the sample space, they're picking 2 specific marbles each. So there's no choices anymore. Okay, so The only way you can get yellow 2, yellow 3 is if you grab the yellow 2 marble and the yellow 3 marble. Okay, so now this is uniform. So now we can compute the probability. Okay, so the probability, and again I'm going to call it yellow, yellow, is going to be the number of ways we can get yellow, yellow over the number that are in the sample space. So here we have to count. Now I wrote out all the ways to get yellow, yellow, so maybe I should highlight that in yellow. Okay, so those are the ways we can get yellow, yellow. Okay, so that's actually that number. Now we didn't fill in all the things in the sample space, but we can use our counting to figure this out. So why is yellow, yellow 3? Because there's 3 yellows and we want to pick 2 of them. So it's 3 choose 2 ways. Now for the sample space, there's 8 marbles in total and they're all different and we want to pick 2 of them. So it's going to be 8 choose 2 on the bottom. So the sample space, there's 8 choose 2 different outcomes. And if we divide those, we get 0.107. Okay, now just to compare, okay, so note, if we did the probability at this point of green, green, those are the 2 that we compared, it's going to be the number of ways to get green, green over the number in the sample space. And this is going to be 2 choose 2 over 8 choose 2. So if you compute that, you actually get 0.036. So our intuition that GG was less likely than yellow, yellow is true. Okay, so this one is less than that one. Okay, so you want to be careful about the sample space. You want to make sure it's uniform. This trick that we used here is one that we will often use. So where you assume you can tell the difference between things, even if you can't. All that's going to do is give you multiple ways that or even more ways that your event can happen. Okay, let's do another example. So, suppose Dylan gets a goodie bag containing 4 wine gums, 3 jujubes, and 8 cherry tomatoes. He's going to draw 3 of these at random, and he can't tell the difference from touch. Okay, so this randomness is saying that he doesn't know what he's picking. Okay, so he just grabs any 3 of them. So our sample space is going to be sets of 3 items from the bag. Okay, and again, we're going to be assuming each item is distinct. In order to get a uniform sample space. Okay, so that means you can tell all these wine gums apart, you can tell these jujubes apart, and every cherry tomato you can also tell apart. Okay, so assume they're all distinct. So that means the number in the sample space. So we have 4 wine gums, 3 jujubes, and 8 cherry tomatoes. So that's going to be 15 things in total. Okay, and he wants to grab 3 of them. So the number in the sample space is going to be 15 choose 3. Okay, now we want to know the probability that Dylan selects at least 2 candies. Okay, so let's let the at least 2 candies be event E. Equals grabs at least 2 candy. Okay, so candy are wine gums and the jujubes are both candy. So there's 7 candies in total. Now, okay, so then the probability of E is going to be, now we're in a uniform sample space, it's the number in E over the number in the sample space. I'm going to move down a bit. Okay, so we already know the number in the sample space is 15 choose 3. Now, we want to count the number in E, so here we're using our counting techniques. So remember, it's easier to count if you know exactly what's happening. So with this at least, he could get 2 candies or he could get 3 candies. So I'm going to split that into cases. Okay, so this is exactly 2 candy. And then I'm going to have another case, exactly 3 candy. So how many ways could he get exactly 2 candies? So there's 7 different candies because we're assuming they're distinct, and I want to pick 2 of them. So I'm going to have 7 choose 2. And then he also needs to get 1 cherry tomato. So I have to multiply by 8 choose 1. Okay, now I want to add, because these are 2 different scenarios where he gets at least 2 candies, where he gets exactly 3 candies, I want to pick 3 of the candies, and if you want, you could say he picks none of the cherry tomatoes. Okay, now if you compute this, you'll get 0.446, I believe. Okay, now one thing I do want to mention here, because we have a plus in the numerator, you could actually split this up. Okay, so that they're over the same denominator, but you add, so you divide first and then add after. Okay, the reason why this might be important is that this is, the first one is the probability of getting exactly 2 candy, and the second one is the probability of getting exactly 3 candy. So you see, if you compute the probabilities separately, you can add them, or you can add on top of your numerator. Okay, it's the same. You get the same answer. Okay, let's try another one. What is the probability that Dylan selects at least 1 wine gum? Okay, so this is doing something very similar to what we did before. If he gets at least 1 wine gum, he could get 1, 2, or 3 wine gums. Okay, so now we're going to have to add 3 different things. Okay, so the probability of at least 1, I'm going to call it W for wine gum, is going to be, so again, I could compute these probabilities separately and then add them, or I can just add on the top. It doesn't matter. So let's do it on the top here. So the sample space is the same. So if he gets 1 wine gum, so there were 4 wine gums, so that means he has to pick 1 of them, but then he also has to pick 2 other things, and there's 11 other things. Okay, now if he gets 2 wine gums, he picks 2 of the wine gums and then 1 of the 11 other things. And if he gets 3 wine gums, he has to pick all of them from the wine gums, and you can have the 11 choose 0 if you want, but you don't need it. Okay, if you compute this, you should get 0.637. Now, we could have computed this a different way. So instead of doing these cases, when we computed the number with at least 1 wine gum, okay, we could have actually used the complement rule. So it would have been the number in the sample space, or the universe, minus the opposite number. So if he doesn't get at least 1 wine gum, it means that he got no wine gums. Now if I simplify this fraction, it's actually n of s over n of s minus n of the number of ways to get no wine gums over the sample space. And this would actually be 1 minus the probability of no wine gums. Okay, this is the idea behind the complement rule. But if we actually compute it this way, it's going to be 1 minus, so no wine gums, means that all 3 of his things came from the 11 other objects. Okay, so it's going to be 1 minus 0.363, which again gives us our 0.637. Okay, so we also have a complement rule for probabilities, and it's very similar to what we had for counting, except instead of subtracting from the universe, we're going to be subtracting from the number 1. okay, which is like the unit, the biggest number that the probability could be. So if you have an event E and you want the probability of E, you could instead do 1 minus the probability of E complement. Okay, or you can, if there's cases, you can do cases. So at this point, now we can finally solve that birthday problem that maybe has been bugging you since the last video. So what is the probability that at least 2 people, okay, in a room of 38 people have the same birthday? So remember, we're assuming all birthdays are equally likely, and there's 365 possible birthdays. So if you wanted to count this directly, so okay, wait, let's just write it down. So the probability of at least 2 with the same B-day is going to be the number of ways that you could have that divided by the number in the sample space. Okay, assuming that our sample space is uniform, which it will be, that's why we have the equally likely, each day is equally likely. So what our sample space looks like is going to be sets of 38 birthdays where you could have overlaps. So it is going to be uniform, so we can use the counting. Now, if you want to think about splitting this up into cases, you could have 2 the same and 36 different ones, or you could have 3 the same and 35 different ones, okay, all the way up until 38 people all the same. But then you, in fact, could, so maybe I should write that, 38 all the same. But then you could even have like there's lots of cases. You could have 2 the same, 2 the same, okay, etc. So there's just way too many cases for this to be useful. Okay, we don't want to do it that way. So what we're going to do is try and use the complement rule. So it turns out the complement is much better. So it's 1 minus the probability. So what's the opposite of at least 2 people have the same birthday? So if you don't have at least 2 people with the same birthday, it means that you have nobody with the same birthday. Maybe I'll just write no same birthdays. Okay, so that means that we want the number of ways that you could have none the same over the total, the number in the sample space. And it turns out that this is actually not too bad to count. So in the sample space, I have 38 people all with a birthday. So each of the 38 people has 365 options. So in the denominator, I'm going to have 365 to the power 38. Now don't try and do this on your calculator one step at a time. These numbers are much too big for your calculator to give you out. So if you do it all together, I think you can get it. It will give you the answer on your calculator. So the numerator, now I still have 38 people, but I need them to have different birthdays. Okay, so the first person has 365 days. The second person has 364 days. The third person has 363 days, etc., etc. This is like a permutation. Okay, so I have 365 permute 38. That's going to guarantee that I get 38 different birthdays, and the order matters because they're going to different people. Okay, so if you compute that, you should get 0.891. Oh, wait, I lied. Sorry. That was my old calculation for 40 people. For 38 people, which is what our class is, it's 0.864. So it's actually incredibly likely that in a room of 38, at least 2 people have the same birthday. Okay, one more example. So suppose you roll 5 6-sided dice. Okay, everybody loves these dice questions. So it's like you're playing Yahtzee. Okay. Now we want to know what's the probability all 5 dice are the same. So here we want to first think about the sample space. Okay, so when we're computing the sample space, the outcomes are gonna be sets of 5 numbers, okay, on the die. So the numbers from 1 to 6 are the only options for each. But we need to assume that we know which numbers came on which die. So what we're going to do, each die, where the 5 die we think of as being colored. So we can tell the difference. Okay, so getting a 5 on the first die is getting a yellow 5, and getting a die on the 4th die is getting a green 5. Okay, so we know where they occur. This is going to ensure that we have a uniform sample space. So that's our sample space, and we want the probability that all 5 are the same. So essentially what we're asking for is the probability you get a Yahtzee on one roll. Okay, so you don't get 3 rolls anymore. Okay, so this is going to be the number with they're all the same divided by the number in the sample space. So how many ways, it's easier to do the top in this case, how many ways could you have all 5 the same? Well, you just pick a number. Okay, there's only 6 options, and once you pick a number, all 6 have to be, all 5 dice have to be that number. Okay, so this is just pick a number for all 5 dice to be. Now on the bottom, we're actually going to have 6 to the power 5. Okay, that's because there's 6 options for each of the 5 dice. So you have 6 times 6 times 6 times 6 times 6. Okay, so once for each die. So if you compute that, you get 0.00077 approximately. Okay, what if we want to know the probability that at least 2 of the dice will be a 6? I'm sorry, exactly 2. I don't know where I read at least 2. So exactly 2 of the dice will be a 6. So we want the probability that exactly 2 6s. So that's going to be the number of ways to get exactly 2 6s divided by the number in the sample space, which we already computed. So we know the sample space is 6 to the 5. So now we want to figure out how many ways could I get exactly 2 6s. So we want to know on which colors the 6s occur. So of the 5 dice, I want to select 2. Okay, those 2 are going to be 6s. So I'm going to write times 1 squared, just so we're clear that there's only one way for them to be a 6. Okay, now all the other 3 dice have to be something other than 6. But they could be the same number. Okay, so they could all be 2s, for example. So there's going to be 5 options for each of the 3 dice. So I'm going to have 5 times 5 times 5. So this is going to be select a number that's not 6 for each of the 3 other dice. So if we compute that, you get 0.161 approximately. Okay, now, what if I know exactly 2 of the dice are the same? Okay, show the same number, but I don't know what that number is. So that's similar to what we did in B, except here I knew the number was 6. Here I don't know the number. And also here I want all the rest to be different. Okay, so I can't have repeats here like I allowed in part B. Okay, so it's similar. So we want the probability exactly 2 the same. Okay, so that's going to be the number of ways that we have 2 the same over the sample space, which is 6 to the 5. So again, I think we want to start the same way. So from the 5 dice, select two dice to be the same. Okay, but now I need to know what number they are. So I'm going to pick a number. So I have 6 choose 1 ways to do that. So this is the number of the pair of dice. Okay, now the remaining 3 dice, I want them to be different, and the order is going to matter. So I want 3 different numbers, and the order is going to matter because the die are different colors. Okay, so you could do it as, okay, the first die has 5 options because it can't be the same as the pair. The other die has 4 options because now it can't be what I just picked. And the other one has 3 options. Okay, this is 5 permute 3, if you will. Okay, but this is select different numbers for the remaining 3 die. And if you compute this, you should get 0.463. Okay, what is the probability that you roll at least 2 6s? Okay, so if you think about cases, that's going to be 2 6s, 3 6s, 4 6s, or 5 6s. So I get 4 cases, one of which we've done, so that's nice, but it's still 3 more cases. We might want to think about the complement here, but you could do it that way if you wanted. Okay, so the probability you get at least 2 6s should be 1 minus the probability of the complement. So if you don't get at least 2 6s, it means that you got less than 2 6s. Because the number of 6s is an integer, it means you got at most 1 6. Okay, so that means that you could have got exactly 1 6, or you could have got no 6. Okay, so then we can compute each of these probabilities. And we need to subtract both of them. Okay, so this minus sign has to go to both things there. That's why I put those extra brackets in. So the probability I get exactly 1 6. I want to pick which die is the 6. So of the 5 die, pick one of them. And then make it a 6. Okay, so there's one way to do that. And then the other 4 die can be any of the other 5 numbers. So I get 5 to the 4. Now for no 6s, it's just that all 5 of the dice can be any of the 5 numbers. So maybe I'll explain that one here. So this is 5 options for each of the 5 dice. Okay, so the options are just anything but 6. Now if you compute this, each of these is actually 0.402 because they're actually the same probability. You subtract both of them, you get 0.196 for your answer. So that's a few examples with counting and probability.